Hi everybody, my name's Brent and I'm the CEO of Sterling Plan B, and we manufacture large-scale energy storage systems. Today we're going to talk about how safety can be impacted by design and also what we think the safety standards are moving towards in terms of large-scale integrated systems. What I'd like to show you to start off with is exactly what can happen here in the element of system scale. So this is a single cell, 75 amp hour at 4.2 volts, that's being overcharged to explosion. So please take a look at the severity of what it is we have to manage in scaled systems. So that video gives you an idea of the magnitude of energy that is contained within lithium battery systems. Now imagine that times 3,900, and that's roughly how many cells and how much energy we have contained within a single megawatt hour system. So we have to take this problem seriously. It's something that has to be managed, and it's something that we all have to meet the expectations of in terms of operating safely. So up until now, the safety standards have really, I don't think, fully addressed the potential scalable event that can occur with large-scale energy storage systems. The expectation was that we would show that if a cell went into a failure and we were managing it safely, that was enough for a pass, and that was something that everybody accepted as good enough. Today, people like the group DNV, the leading integrators and type approval standards for batteries worldwide, has ramped up that standard effectively. Instead of just demonstrating a battery failure, but now we're demonstrating a thermal runaway within a battery failure. So effectively what you just saw in that video is what the new standards are forcing us all to address in terms of delivering safe and manageable systems. And that's the whole purpose of this, is to avoid situations where you have large-scale fires or large-scale explosions, or also just the release of a lot of gas that's extremely toxic and nauseous and can cause people a lot of illness. So if you look at the bottom picture here, we're about to watch a video on a nail penetration test, which is a very destructive test, and you'll see a little bit more, and we'll talk a little bit more about that. So here, this is me actually punching a nail into a battery. It's nothing I'd recommend that anyone does, unless you're very comfortable with your system, but watch what happens. So that was a pretty dramatic event, but not the ball of fire that you saw in the previous video. So we do know that a good thermal management system can actually help to manage a thermal runaway. What you see here is the result, in that the single cell that had been nail penetrated was completely combusted and consumed, but the propagated cell number 2 in this case, only saw a temperature of around 80 degrees. So cell number 1 failed at around 800 degrees, and if there hadn't been a good thermal management system, that explosion you saw at the beginning of the presentation is exactly what you would have seen, where with a good thermal management system, cell number 2 didn't even come close to igniting, and so we could have had this kind of a failure, but safely managed it out to the customers and the passengers' benefits. So how do we avoid a fire? The McMicken facility in Arizona Public Services was the victim of one of the largest battery explosions in the world to date, and there were several people who were hurt. One of the firefighters was thrown around 75 feet into a fence, and of the 4 people who were injured, 2 men suffered sustained traumatic brain injury, so obviously was not managed well enough. The suspected fire was actually an extensive cascading thermal runaway event, initiated by an internal cell failure within one battery cell in the energy storage system. It's believed to a reasonable degree of scientific certainty that this internal failure was caused by an internal cell defect, specifically abnormal lithium metal deposition and dendritic growth within the cell, i.e. a failure that couldn't have been predicted with the design and engineering of a battery, but could have been better managed with a better designed battery and better designed firefighting system. So the event happened over a period of time, and it became worse as the event was both exposed and they opened up the room to try and get into the space, and the gas that was now being generated by many cells was again ignited. So let's take a look at what we can do at the cell level. Is the cooling system you have effective? So today there are effectively air-cooled systems, semi-air-cooled systems or semi-liquid cooled systems, and liquid cooling systems. The challenge we face with air cooling is simply managing to maintain the temperature of the cell at a level that's going to both help manage a fire or an explosion and simply prevent it. And air cooling requires about 3,200 times more air than liquid in order to manage temperature. If you have a liquid cooled system, you have a much better avenue to effectively managing the performance of the cell and the internal resistance that can be developed. But the liquid cooling itself has to be built to enable you to cool effectively faster than the lithium cell can create energy. So, when cells develop dendrites, this doesn't happen at the original stage of installation or manufacturing. It happens over time, and it's a natural part of the evolution of a lithium system. So not only do you have to be considerate of your cells, but you have to be considerate of what's that dendritic development going to be over time. How much more heat is going to be generated as the system ages. Now, one of the ways that you can help manage that is by having your cells in series with voltage and temperature sensors on each one of the cells. When we do this, we have the ability to both observe the voltage and temperature of the cells, effectively preventing or at least managing the aging of the cells and visibly seeing how they're being affected, so that we can observe on a cell-by-cell basis exactly what's happening within a system. Now, how are you managing that? If you're dealing with a lot of small cells in a megawatt scale system, it's virtually impossible to monitor the temperature and voltage of each one of the cells. When you get into the bigger cells, you are dealing with more energy within a smaller amount of space, and so the inherent risks of the safety systems that are designed to incorporate this are going to be a challenge. And then the issue of how do you actually make propagation work. So in a lot of the design of energy storage systems today, especially where you're dealing with air-cooled systems, they're using plastic cell carriers and plastic barriers between the cells. That's perfectly okay for normal operation, but plastic has two issues with it when it comes to being something between the cells. One is it tends to prevent heat transfer, so it makes it more difficult for the heat to be dragged out of the cell. And the second thing is that how can it resist the temperature that can occur? A lithium cell can reach a temperature of 1,000 degrees on a spontaneous eruption, and that is something that plastic is going to have a very hard time managing. So we have gone down the road now of using metal cell carriers with metal barriers between, with about a 2 millimeter space at the top of the cell to prevent propagation from occurring if a cell does catch fire and explode. Then we have the issue of how do you actually manage the risk, and how do you monitor the state of health, how do you monitor the performance? Again, by going back to the principle of one voltage and one temperature sensor per cell, we can now build the algorithms in place that can actually see what variations in the temperature and voltage are going to do to the lifespan of the cell, and ultimately to when could the cell potentially fail. Most lithium failures are not spontaneous, they're predictive and they occur over time. So monitoring is something that's really challenging and it's expensive, but it is key to operating the system safely. And then you have to deal with the gas. So in a lithium fire, the gas extraction and gas management is really where the most critical element occurs. You've already had a failure now. Your cell has failed and is producing gas. Do you expose that gas to the room that the cell is in, which is what happened at the McMicken facility, and then when they opened the door they caused a spark that caused an explosion? Or do you have a way of extracting and managing that gas unique to the environment that the battery is in, so the gas can be safely managed, extracted, measured, even burned in a burning box before it gets exposed to anything? This way you can naturally disperse the gas to a much larger volume environment other than something like a container. And if you can do this, you can effectively make the battery room a safe place to operate and work in, even if you are seeing a battery failure. Then we deal with the issue of third-party firefighting systems. There are some very effective ways to manage lithium fires. There are some excellent two-part foam systems that can contain a lithium fire. Very expensive to install. Do have some service and maintenance elements that have to be contended with. And then there are conventional firefighting systems, like gas firefighting systems, or foam firefighting systems, or simple chemical firefighting systems, or water mist systems, or sprinkler systems. All of these systems have the problem of durability. If you can't effectively surround the lithium fire with something like a two-part foam, there's almost no way to make sure that you have enough reservoir material to continue to extinguish a fire for the durability that it can have. Lithium fires can generate their own oxygen. They're very difficult to extinguish, and most conventional firefighting systems aren't really going to solve the problem, again, unless you have a significant volume of ability to manage the fire. So it's better if that firefighting is built into the system itself. When you look at the other side of it, it is the software. So could software prevent thermal runaway? No. Can software predict thermal runaway? Yes. So your battery management system has to be designed to effectively manage the fire before it can occur, and you have to have the risk protocols built into the operation of the system to ensure that the alarms and the operating conditions and the training are driven towards making sure that we proactively manage instead of reactively manage anything that could be a firefighting failure. We can do that today with a lot of very sophisticated but usable software. In our case, we monitor the cells at the cell level, no matter how large the system is, and it's that management at the cell level that effectively allows us to proactively prevent fire from occurring. This management system, though, has to be enabled to be operating continuously. You may not be using the energy storage, you may have turned it off, but because a lithium cell is a chemical reaction and it's an organic process, it's never off. And your battery management system has to be active and up 100% of the time, and able to communicate with the system's owners to ensure that they have full understanding of how the batteries are operating. Now, we look at the operations of the system. There's some simple things that we can do at the operating level to make sure that everybody is safe. In our case, we actually add contactors within each one of the modules to make sure that the positive and negative power terminals are completely isolated until the cables are all connected, and the BMS has actually determined that the sequencing of the cables is correct to prevent a dead short, and then it will allow the contactors to close and generate voltage and energy onto the grid of whatever it is we're connected to. We believe strongly this is going to become the ultimate standard to make sure that you both limit the voltage risk that you manage to whatever a single module voltage is, in our case 100 volts DC, and systems that are quite often up to 1500 volts DC. That's a very important feature. And also that when someone does make a disconnection, that's going to cause the whole system to shut off so that there is no voltage at the terminals. This is also good for transit, so there is no voltage on these terminals when you're transporting, installing, or hooking up. It's only when everything is completely closed system that the batteries can actually deliver energy and power to the grid. Then we have other elements. We believe strongly that every battery string or every battery system, so a series of, let's say, 1000 volts, should be protected by a breaker, and that there has to be an electric stop, software stop at every single one of the control units to prevent the batteries from reacting with the grid if they need to be shut off immediately. Everything should be at least IP20 in terms of the connectors themselves, so people can't inadvertently put their fingers in if there is current or voltage live at a terminal on a battery. And there does need to be an HVIL interlock at each system. Then you have to make sure that you size the system correctly. So today, people are caught up in the concept of buying everything by the kilowatt hour without necessarily understanding the full operational risk that they're taking on by making a decision on that matrix. And the truth is that every battery company delivers cells and systems that have different performance capabilities. So the temptation to deliver a demand energy capacity that somebody has without understanding how that's going to immediately be impacted by the cells and the battery you've designed is the risk we all run in making systems incorrectly sized for the applications they've been designed to, and ultimately that's going to force them to age or fail faster and put the cells at risk. What we have here is a picture of a cell that has been aggressively aged through charge and discharge, and as you can see, it started to bloat. Once they start to bloat like that, again, there's no way to do anything but allow the failure to occur, and you have to manage it safely. Now we take a look at what can service do to support this. So it's vital that the crew are able to look at everything within the battery. So there is a large contingent of battery suppliers that are putting rear-mounted connectors for water systems and power systems and communication systems. We strongly believe these need to be visible connectors that you can actually service and support. There should always be a display on each one of the battery strings so that you can actually dive into the battery and see visible alarms if anything has occurred. And this way you have a system that can be serviced in the battery room by the crew that are trained to do this, and you can actually train them much more simply. You're not reliant upon remote monitoring or remote access to be able to guide people through critical safety and service support functionality. Then we have to train the actual crews on board. So if you have a crew on a site, you do need to train them on how to operate their system safely. You have to train them on how they can manage a fire if something does occur, and what do they do in almost every scenario. And not only the crew of the application themselves, but call it the contingency crew, your local firefighters. These people all need to be involved because energy storage is going to become a much bigger part of society, whether it's in your car, whether it's in your ship, whether it's in your microgrid. It is a part of what we are all having to learn how to deal with, and these people all need to be trained properly, and we owe them the responsibility of giving them that training. Now, propagation, that is the problem. How do you manage propagation? The good thing is the current testing regime that's been introduced by D&D last year really does force all of us as battery designers and engineers to deliver a system that can pass this where you don't have propagation. And by introducing a thermal runaway at the cell level and determining whether or not you have propagation, you really are creating the best possible test possible that does reproduce the worst thing that can happen in the field. So from here, true safety, true design, and true standards can really be evolved. I'd like to thank you all very much, and everyone please have a great day.